So here's a leftover example from the previous section here. Try it. I'll just let you pause for good so you can take a look at that. That's related to what we did in example 9 using the addition rule. We move over to the multiplication rule and the formula for conditional probability. And so here it is. It looks very complex, but I want you to keep in mind again that vertical bar represents the probability of B given A already occurred, and we have a formula for that, right? We found these out again using kind of our not intuition, but using the contingency table and identifying the new given part, right? That becomes our new population, right? It's out of that, right? Out of that many from that event, right? Given that he was a male, given, right, in that situation we did before. So independent. Two events are independent, right? So now we have this term. If we're going to deal with conditional probabilities, then we have to analyze situations where what's the probability of B occurring given that A already occurred? Now, if two events are independent, meaning there is no connection, then the probability of B happening will be just the probability of B happening, right? Even if A already occurred. We don't have any way to, there is no influence of A on B, and so we have just the probability, right? So in this case, right, to summarize, meaning knowing that the outcome of A has no effect on the probability of B is kind of highlight here. Meaning the probability remains unchanged when we know the outcome. So that definitely two different ways to think about it. And of course, you may even see the formula the other way around. So in this case, you may see this too, right? The probability, if I can get this in there. Sorry about that. The probability of B is equal to the probability of B given A. So again, you can see those back and forth either way. And so looking at some examples here. So let's take a look at what we have up here now to do this example with that formula. We can also, again, think about the way we've done before. So we can use the formula as we can see here. And so we have a scenario where you have, and again, what this looks like is when you get your medicine, it has different types of labels. Do people give the right dosage depending upon the labels, right? Again, it's a little bit more complex scenario here. But what's the probability of getting a correct dosage? It's 13 out of 28, right? There's 28 total outcomes here. 13 and then 15, here's your 28. Now, what's the probability of getting a correct dosage if you're in the hospital, given that there's a ratio label versus a concentration label? Each medicine has a different type of label, right? Different potential types of labels. Given that you got a ratio label, in this case, this is 2 out of 4, right? Because there are 14 total. Given that, right, out of ratio labels, there's 14 ratio labels. If you look at those right there, you end up with 14, and there's 2 out of the 14 are correct. And so you have that. We could have also done the formula, right? So again, we went back to how we were doing. We can also look at the formula here and say, what's the probability of B given A occurs? That's the probability of A and B, which is 2, divided by the probability of A, right? And A in this case is that you have a ratio label, right? And so looking at probabilities like that, we could also get this answer here. So I've done the mathematics here. If you look carefully, actually calculate the probabilities using the formula, and you get 2 out of 14. The probability of A and B is 2 out of 28. Probability of A occurring, right, getting a ratio label, is 14 out of 28. And then when you divide those two fractions, you get 2 out of 4. And so you can see getting a correct dosage and label type, they're independent, right? Sorry, they are dependent, because when you calculate those two values, right, when you calculate them, they are not the same. And so you see they're independent if they're equal, but we just calculated both of them separately. And the answers are they're different. And so we say they are dependent. Giving the correct dosage depends upon which label you get. And so knowing that we have a racial label, we decrease the probability of correctness. You can see here, given that it's a racial label, which again will be an indication that maybe something's up and we need to change our policies based off of that. This leads us to our last section here, which is the multiplication rule. And it's a way of calculating AND problems based off of the formula we have over here for conditional probabilities. And so you can see again we have this AND. Now if events are independent, then technically we can just multiply those individual probabilities.